Hello. Welcome all. I'll wait around 10 minutes. Maybe a student will join. Then after I'll start. Okay, no one joined, so let us start. I'll upload the video and please go through the video and solve one by one questions. So now let us start. So the first question is about the exact analysis of viscous flow problem can be done by exact analysis. We are talking about here the exact analysis. Exact means what here? Let me discuss. So the exact analysis means nothing but, let us suppose if water is flowing, if this is a channel or river you can say, or pipe, you can take the example of pipe also, pressure flow. So this flow having pressure force, another gravitational force, or you can say the body force, another shear force between the layer of the fluid particle due to the viscosity. You can say the viscous force also, right? So exact analysis means we analyze all these forces during the formulation of flow in terms of mathematical equations. You can say the continuity equation, Bernoulli's equation, all Navier-Stokes equation, all are the mathematical formulation of the fluid flow and the physics of the fluid flow. You can say the physics of the fluid flow. Now we want to do exact analysis here. So if I talk about the continuity equation, you know already. If I write the differential form, du by, if this is u, du by dx, for here is a certain, let me write for rho by dt plus rho du plus rho v by dy plus del rho w by del z equal to 0. So this equation is for unsteady continuity equation. Differential form of the continuity equation, unsteady flow and compressible flow. This formula is applicable for unsteady and compressible. When we will do steady flow, steady and compressible, then this will be 0. Steady because fluid characteristics change with time will be 0. Now if you want to do steady incompressible, then rho will be cancelled out from each term. So your formula will be become for continuity equation for steady incompressible. Okay. So Bernoulli's equation you know already, P by rho z plus V square by 2z plus Z is equal to constant. So here is the meaning is whether this equation is having the term of viscous force, no. So but here we want to do exact analysis of the your fluid flow or viscous flow we are talking about, and in this equation the viscous force is not considered. So this equation cannot do the exact analysis of the viscous flow. What we will do, we'll go by the Navier-Stokes equation. Navier-Stokes equation incorporate all the forces. If I write the formula for Navier-Stokes equation, so all forces, first of all, Navier-Stokes equation or Bernoulli's equation basically we derive using the your second law of Newton, moment force is equal to mass into acceleration, or you can say the if the body is falling from above to down. Okay, so here forces is your pressure force. So Bernoulli Navier-Stokes equation we write like here I have written already, del u by del t, or these things you can write in terms of, if I write Navier-Stokes equation in x direction, it will be y direction also, it will be z direction, all three direction. But if I write in the x direction, your formula will be like that, del u by del t plus del u by del x plus v del u by del y plus w del u by del z. These things I have written here equal to minus del p by del x plus mu these things then u square plus rho zx. These things how you will write, mu will be outside and del square u by del x square plus del square v by del y square plus del square w by del z square. So this is the whole equation, x direction. Similarly for y direction, let me write here for you. So I have PPT also, so I want to write here for each direction how it will look like. So basically Navier-Stokes equation is a very famous equation for solving such type of problem, Navier-Stokes. So in x direction how you will write, in x direction your equation will be del u by del t plus del u by del x v del u by del y plus w del u by del z equal to minus del p by del x plus mu del square u by del x square del square u by del y square del square u by del z square minus plus rho, this is your body force, this is body force, this is your viscous force term, this is your pressure force, and this is your acceleration. Here is the rho term, this is your acceleration, this is the local acceleration, this is convective acceleration, and this is your mass term, that is rho. Rho is equal to mass by volume, so this incorporate your mass term. Hope you got it. X direction. Similarly in y direction you can write, in y direction how you will write, rho will be common, so del v by del t plus u del v by del x plus v del v by del y plus w del v by del z equal to minus del p by del y del p by del y plus mu del square v by del x square plus del square v by del square v by del y square plus del square w by del z square plus rho z y. Similarly in z direction, remember please this equation is very important, so you need to understand. You can go through video lectures how sir have discussed about that. The z direction, that is your w by del t plus u del w by del x plus v del w by del y plus w del w by del z equal to minus del P by del Y plus mu del Z here, not del Y. This is del Z, mu del square W by del X square plus del square W by del Y square. Please you write on your copy 2 or 3 times, then you can easily understand. By your understanding, whatever I have tell you here, this is a body force, this is your, okay, I'll discuss. Del square W by del Z square plus rho zy. So this term your body, here Z also, body force. This term is your viscous force. This term is pressure force. That is summation of force is equal to what? Mass. This is rho represent your mass and this represent your acceleration. This is your local acceleration. This is your convective acceleration. So this A represent your, in case of fluid mechanics, having two things, local acceleration when you will solve your problem using the Eulerian description, and convective acceleration. So hope you got it about this question. Why we use the Navier-Stokes equation for complete analysis of your viscous flow problem. Now the second question is, the major difference between Navier-Stokes equation, and Euler equation. Euler equation is the dissipative transport phenomena. The impact of this phenomena is in a system is like you have a problem and you are going to solve this problem using the Navier-Stokes equation and the Euler equation. The impact of this phenomena, that is, so what will we actually, here we are talking about, if you will see the options, entropy and internal energy. What will happen about entropy and internal energy when we will solve this your a particular problem using the Navier-Stokes equation and the Euler equation? So this is the question. Just to please think about it. If you not know about the Navier-Stokes equation and the Euler equation, so still no one joined. If you not know the Euler equation and the Navier-Stokes equation, you please go through video lecture so you can easily identify about the Navier-Stokes equation and Euler equation. So here when we will utilize Navier-Stokes equation and Euler equation for a particular problem, the entropy will be, if I show you, entropy will be increased. Why? Because dissipation is a fundamental concept in the thermodynamic and the physics that describe the process by which energy is converted from one form to another. Dissipation is a fundamental concept. Like your mechanical energy is converted electrical energy or the thermal energy, you can say. So this actually the in physics the dissipation term is used for describe such kind of thing, typically resulting in an increase in the entropy of the system. It means typically resulting in increase in the entropy of the system. Means entropy is defined as nothing but is a measure of disorder or the randomness is the system in the system, and it tends to increase over time in natural process as described by second law of thermodynamics. So this is the whole concept behind your entropy when you will use the Navier-Stokes equation and Euler equation for a particular problem. Entropy will be increased. That is the disorderness of the system will increase. Now, the question number third. In case of laminar flow of viscous fluid between two parallel stationary plates, here is the two stationary plate. Here is the case of both are the stationary plate, not moving, and parallel. Here is written the parallel. So it is parallel to each other. Okay. The ratio of here is the ratio of maximum velocity, the ratio of maximum velocity and average velocity. What will be the solution for this? Now the another question here I want to give you. This is a famous question. If the pipe is circular, if the flow domain or circular, let us say pipe, then what will be the value of laminar flow I am talking about? The V maximum divided by V minimum, V average. In case of pipe flow, in case of parallel plate flow, what should be the value? Just think about it. So you can pause the video. Let me discuss the answer. So basically in case of your pipe flow, your velocity diagram you have seen like that. In case of laminar, this type of, this is your maximum, and you will take average, maybe it will come like that. This is the average velocity and this is your V maximum. So V max is 2 times of the V average. Theoretically, similarly, here is the V max is 1.5 times of V average. Remember please. So in case of parallel plate, your the average is V max divided by V average is equal to 1.5, and here is the answer of V max minus divided by V average, it will be 2. In case of pipe flow, here is the in case of parallel plate. Fixed plate. Remember please. Now the next question is, here you can see the analysis. The formula is U max is equal to h square divided by 8 mu del p by del x, and U average is equal to minus h square by 12 mu del P by del X. Now the next question is question number 4. In a laminar flow between two fixed parallel plates, here is again laminar flow between two fixed plates. The flow is laminar. Parallel plate. The shear stress distribution is shear stress. I am talking about shear stress. You might be heard about this equation. Constant across the passes, maximum at the center and zero at the boundary. Zero all through the passes, maximum at the boundary and zero at the center. So constant across the passes means what? Your shear stress distribution will be like that, constant throughout. This type of constant. This is option A. Option B, maximum at the center, maximum at the center and zero at the boundary, like that. This is option number B. Option C, zero all through the passes. It will be zero. Nothing value. Nothing. Maximum at the boundary and zero at the center. This is option C, and option D your maximum at the boundary and zero okay and zero at the center. So which option will be correct here? Question number 4 is like that. So tau is equal to, just please think you, del u by del y. This type of question you might be seen in the previous year gate questions as well as your assignment question also. So here is the correct answer is your D, maximum at the boundary and zero at the center. That is your option number D. Such type of distribution of shear stress you can see in the between two parallel plate flow. Now, what is the actually formula here? This R is nothing but represent your tau, that is shear stress. Shear stress this is representing. The formula is half del P by del X H minus 2y. At y equal to 0, And if your y is equal to 0, means what? Your r is equal to half h by 2 del p by del x. Right. At y is equal to h by 2, r will be become, here if I write you, half del p by del x h minus 2 into h by 2. 2 cancel, it will be 0. So it means y is equal to h by 2. That means if you are taking y from, this is your x direction, this is y direction, and this is whole h. So if this is your h by 2, when your y is equal to h by 2, what will happen? If you will see here at the middle, when you will go at the middle, this formula is given, your r is 0, that is your shear stress is 0. That means when you will move from the bottom h by 2, your shear stress will be 0, and when y is equal to 0, that is here your shear stress is maximum. Similarly, when you will come from this side h by 2, this will be maximum and this will be 0. Remember, please, always remember, in case of pipe flow, similar kind of distribution will be there also in pipe flow. Shear stress, remember, magnitude may be different and other thing, but distribution should be like that. Next question, question number 5. When fluid is at rest, means let's suppose a pond. In the pond, water is rest, there is no moving, no motion in the fluid flow. Okay, the only stress acting at any surface of any fluid element is whether hydrostatic, whether viscous, whether local hydrostatic, or whether viscous stress. So these two things. This is a filling the blanks. We need to fill the blank using the, it may be here is the two only, local or the viscous, local hydrostatic pressure or the viscous pressure. Which should be here? You just think. I'll read again. I'll read next. Which always act inward and normal to the surface. When a fluid is moving, that is now a channel if I consider, and fluid is moving in this direction. This is the cross-sectional area. Let us suppose the rectangular at 1, 1. At A, if this is rectangular, section A representing, if this is rectangular and water is flowing up to that much, here is water is moving, this is not. So filling the blanks, that is pressure or viscous stress is still act inward normal, but may also exist whether viscous stress, whether normal stress, whether pressure, which should be exist. This is an analytical question. If you have conceptual understanding about this subject, during whatever sir was taught in the previous weeks, then you can very easily give the answer of this question number 5. Otherwise it will be very difficult for you. Or in the assignment section, this is the live TA session. I have also discussed about such type of problem in the year, I think in week 2nd, week 2 or week 3rd. So please just try to give your answer. Just think on that. Anyone join still or not? Still not anyone join. Might be network issue. Another. Okay. So in case at the fluid is rest, your viscous stress or shear stress will be 0. But hydrostatic pressure or local hydrostatic pressure will be exist. That is the stress. Here we are talking about stress. It may be normal, it may be shear, it may be press, it may be other stress. Not we are talking about here shear stress. Your local hydrostatic, that is stress due to the local hydrostatic pressure will be exist if your fluid is rest. Filling the blanks. Here is the local hydrostatic. Then when the fluid is moving, then pressure exists or local hydrostatic pressure will be exist, but at inward normal, but your viscous stress also exists. So here viscous, here pressure, here local pressure, or you can say pressure only. So pressure local, this will be not, this will be also wrong. So pressure and the viscous, this is correct. A option will be correct for this. So hope you got it. Here is the when a fluid is at rest, the only stress acting at any surface of any fluid element is the local hydrostatic pressure. When a fluid is moving, the pressure is still act inwardly normal, but viscous stress may also exist where we have introduced a new tensor called the viscous stress tensor or the gravimetric stress tensor. Remember please. Now moving ahead with the question number 6. Question number 6 about very simple thing. The Laplacian operator in the Cartesian coordinate. So we are talking about here Laplace operator in terms of Cartesian coordinate. If I draw here, just for sake of understanding, this is x direction, this is y direction, and this is z direction if I take it. And this represent your I cap, this represent your j cap, this represent your k cap. So now I want to know from your side what should be the value of this Laplacian operator in terms of Cartesian coordinate system. Please think on that. Okay, you can pause the video. Let me discuss first because it is very important. You have seen everywhere such type of operator. The application of such type of operator if you will go through the mechanics things. So now del is equal to, you know already, del by del x I plus del by del yj plus or you can say the vector also, I vector, j vector, and this is k vector, delta by delta z. So this is, but if we talk about del square, this is like that. What we will do? We'll multiply the things. Del by del x, let me write in the vector form, plus del by del y plus del by del z into del by del x plus del by del y plus del by del z k. When we will, here is a dot product, not cross, because in terms of vector calculus there is a different meaning of dot product and the cross product. You might be hard. Okay, when we will multiply these things, I and I, it will be, you know already, I into I will be 1, I into j will be 0, whatever. J into j will be 1, but j into k will be 0. J into I will be 0. If the same things will be multiplied, then it will come 1. So this will give you del square by delta x square. This and this will be 0. This and this will be 0. Now coming on this, del y by del del y j and I will be 0, and this will be 1. So del square by del y square and j into j will be 1. Again j and k will be 0. K and I will be 0, k and j will be 0, but k 1, so that's why it will be remain del square by del z square k 1. So finally your answer will be del square is equal to del square x square plus del square y square del square z square. Remember, please, always remember. So this is the whole concept behind this question. So if you are going to take something like the gradient of something, del by phi, the phi is a scalar quantity, this is a vector quantity. So this multiply is known as the gradient. If you are going to take the divergence of something, this is a vector quantity, this is a vector quantity, this is divergence. Divergence of vector v, the gradient of phi. So gradient, let's suppose your phi is equal to xi, phi is equal to xyz. So your gradient will be like del by del xi xyz, del by del yj xyz. Here is the del phi I am writing, and del by del z k x y z. When you will multiply, you will get what? YZI plus here your XZK plus here XY, here is a J not K, XYK. Such thing you will get the gradient of. That is, so divergence, that is the gradient of something, give you the what? That is the vector. The divergence of that is your, when you will multiply your del operator any vector, so it will give you the what? The scalar. Remember please. So now we'll move on the next question, and the cross product, how we will write the cross product, here I want to discuss also. How I will write, if u is the vector, u is the ui plus vj plus wk. So this is I j k del by del x, del by del y, and del by del z minus u v w. The application of these things I'll discuss in the coming questions. So remember please how we'll write. This is the cross product. And just simply take the determinant of this. I, when we will take I, this will become del w by del y minus del by del z. Similarly minus. Similarly you will take the determinant whatever you have studied in your 12 standard or 11 standard. Now I'll discuss the question number 7. Question number 7 is about the differential analysis of fluid flow problem can be used for calculating the pressure field for a known velocity field, calculating both the velocity and pressure field for a flow, known geometry and known boundary condition. Third, C, calculating both the velocity and pressure field for a flow of known geometry. Option D, both A and B. So here is the question. So I'll take here the 5-minute break, so student can think about it, about the question, and then I'll discuss after the break. Hello, I am audible? Hello, Krishna, just confirm me whether I'm audible or not. I have already solved the 6 questions, so you can follow the video when I will upload on YouTube. Yeah, okay, that's good. Okay, now I'll move with the question number 7. The question number 7 is about, you can write your answer in the chat box. Okay. So question number 7 is, the differential analysis of the fluid flow problem can be used for calculating the pressure field for a known velocity field. Option B, calculating both the velocity and pressure field for a flow of known geometry and known boundary conditions. Calculating both the velocity and pressure field for a flow of known geometry. Option D, both A and B. Which option will be correct? If you have any idea about this, you can write your answer in the chat box. Question number 7. So the question number 7, we use the differential analysis for calculating the pressure field for known velocity field and for both velocity and pressure field for known geometry and the boundary conditions. So option here A and B will be correct. The explanation is, the differential equation of motion in both Cartesian and the cylindrical coordinate. There are two type of problems for which the differential equation, that is continuity and Navier-Stokes equation, are useful. First, calculating the pressure field for known velocity field. Second, calculating both velocity and pressure field for flow of known geometry and the known boundary condition. So here I want to show you, or I want to tell you just few things. We have the 4 unknowns, that is u velocity and v velocity, w velocity and pressure field. We have this unknown. We have the Navier-Stokes equation in 3 dimensions: x dimension, y dimension and the z dimension. We need additional one equation for solving these, for calculating these 4 parameters. So that's why we need your continuity equation. That's why we need the continuity equation for, that is the 4 unknowns and the four equation. But it is not easy for calculating. If you know the 4 equation, you very easily you can calculate. This is not, because Navier-Stokes equation is a partial differential, that is the non-linear partial differential equation, which is very that is the analytical solution of a complex problem is very difficult. Remember please what I am telling. So that's why we need the lots of solver, turbulence solver and all. This is a vast, that is the advanced fluid mechanics. You, if you heard about the CFD things, generally we discuss in the advanced fluid mechanics, not at the graduate level, undergraduate level. So okay, so this is the additional information about the Navier-Stokes equation and the continuity equation and your fluid flow characteristics. Now we'll move ahead on the question number 8. Question number 8 is about, the velocity field in an incompressible flow is not affected by the absolute magnitude of the pressure. but only by the pressure difference. Which is true or false? You try to give your answer. The velocity field in an incompressible flow is not affected by the absolute magnitude of the pressure, but only by the pressure difference. So please try to give your answer in the chat box whether it is correct or true or false. Question number 8. So here is the correct answer of this question is, might be Krishna have lost the connection. Okay, so let me discuss. The velocity field we are talking about incompressible flow, that is your rho does not change with time. Rho is constant. Rho is constant, not time and all, because this is the steady and unsteady condition, but here we are talking about incompressible only. And the absolute magnitude of the pressure means what? That is whether it will be minus or plus, there is no meaning. Absolute means only this is your mod value, that is a plus value, absolute pressure, but only by the pressure difference. That is your velocity field in an incompressible is affected by your pressure difference only. That is these things, if I show you here, these things, the pressure difference things, not by the absolute, because we use in the Navier-Stokes equation I have discussed earlier the minus del P by del X. We have used some these things we have already discussed in the question number first. Rho square V vector, here is the del Vy del T in X direction. Remember please. Okay, next question is question number 9. Which statement is true? Both stream function and the velocity potential are vectors. Both stream function and the velocity potential are a scalar function. Stream function is a scalar and the velocity potential is a vector. And next thing, the stream function is vector and the velocity potential is scalar. Which option will be correct for this? Question number 9. Whether he is joined or not? Yes. So Krishna, you want to say something? You're okay. So please try to give your answer for question number 9. This question is about the stream function as well as the velocity potential function, whether it is vector or a scalar function. You can write in the chat box which option is correct. So you have time little bit. Just think and write your answer. Okay, you are telling the option number D is correct. The stream function. Stream function is vector and the velocity potential function is scalar. Okay, you are telling. No. If you heard about the stream function, whatever the question, let me discuss first with whatever you have seen in the fluid mechanics the question. If you know phi and these things. Okay, so you are telling which option? Let me just see. Or D you are telling. Okay, so here is the both stream function and your velocity potential function are the scalar function, not the vector. Stream function is not the your vector, it is also a scalar function. So I will discuss in the below questions. I have related similar related type of questions, so I will discuss in that question about this statement, that is the why the stream function and the velocity potential function is scalar. The next question is question number 10. The equation of motion for a laminar flow of a real fluid is known as Euler equation, Bernoulli equation, Navier-Stokes equation, and the Hazen-Pauli equation. The equation of motion for laminar flow of a real fluid is known as. Here we are talking about real fluid. So please think on that and try to give your answer. Okay, the answer of this question is the equation of motion for a laminar flow where real fluid we are talking about, that is the viscosity will be there in the fluid. So that is the viscosity is existed in the fluid. We are talking about the real fluid here. That's why. So for solving the real fluid, we need three type of force. That is pressure force as well as your body force as well as your shear force, or you can say the tau f. Okay, so that is your Euler equation and the Bernoulli's equation and the Hazen-Pauli equation not able to solve, not consider these three forces. So but Navier-Stokes equation consider all three forces, so that's why we use the Navier-Stokes equation. If you not know the how we'll derive the Navier-Stokes equation, please follow the lectures whatever sir is taught in the previous assignments, the previous weeks. So the next question is question number 11. The two-dimensional fluid element in the xy plane, the vorticity is given by, we are talking about here vorticity. What will be the value of vorticity? So please just try to give your answer for this question. Question number 11. You have 2-3 minutes. Just try to think and try to give your answer. Okay, we are talking about here the vorticity. So let me discuss. So vorticity is nothing but this is the vorticity is just 2 times of, I think, your rotation omega. Okay. So how you will calculate first of all omega, that is your rotationality. So omega is nothing but half I j k del by del x del by del y del by del z u v w. What I am writing here? I am writing these things. Here I can write also. So how we will calculate? Half is this side and we'll take I. So del by w by, this is just determinant here, del by del y minus del v by del y minus j this side del by v by del x minus del by u by del z plus k del u by del v by actually del v by del x minus del u by del y. So here we can write these things, half I del w by del y minus del v by del y, not y, I think here I have done mistake little bit, z, this will be z, minus, here I want to put the plus, I have taken the minus outside, so what will be, here little bit change, del u by del z minus del v by del x plus k. Why I have done these things, that is I have taken the minus common outside, I'll tell, and del v by del x minus del u by del y. So this is, you can write half wxi plus, that's why I have written here wy, I can write very easily plus here, and j and wzk. So this is your vorticity, similar like that. If I write the vorticity, your vorticity will be, that is the 2 times of your omega value, so it will be wxi plus wyj plus wi, this here, not here, j here, and the wzk. So here we are talking about in the xy plane, so that's why xy plane your the vorticity will be, that is the w z value, so it will be del these things only, del u by del v by del x minus del u by del y. So hope you got it. In 3 direction, if we talk about, so in 3 direction all 3 component will be there. If I write the vorticity in all 3 component, that is w by del y minus del v by del z plus del u by del z minus del v by del x plus del v by del x minus del u by del y. So this is the vorticity in all three directions. Hope you got it. The next question is, okay, the next question is, here is a cross. An oil of viscosity 8 poise flow between two parallel fixed plate. Flow between two parallel fixed plate. Okay, here is flowing oil of viscosity is given already 8 poise, which are kept at a distance of 30 mm apart. 30 mm, that is 0.03 meter. Find the rate of flow of oil between the plate if the drop of pressure in a length of 1 meter, if I write this is 1 meter, and here is the P1, here is the P2. So drop in the length of 1 meter be 0.3 into 10 to the power 4 Newton per meter square. If I take the difference between P1 and P2, it will be 0.3 into 10 to the power 4 Newton per meter square. This statement is telling these things. The width of the plate is 500 mm. W is given, that is this direction. If we draw this direction thing, the width is given. This is the width. Width is given here, this value, width is given 500 mm. That is 0.5 meter. Okay. The flow rate you need to calculate. These things will. So please just think on that. I have discussed a lot. Just I have given the hint you. So you please try to give your answer, then I'll discuss about it. Okay, let me discuss. So here is an oil of viscosity of 8 poise. So here first of all we need try to calculate discharge is equal to your velocity into area. So area we know very easily. What is the area? Cross-sectional area. So width is given already and depth is given already. So area you can very easily calculate. But now how you will calculate your average velocity? For calculating the average velocity, you need to remember the formula between parallel two plate, the pressure difference formula is 12 mu u average into L divided by h square. This is the formula. How it come? You need to go through the recorded lecture. So here is pressure difference is given already 0.3 into 10 to the power 4. 12 is already 0.8 twice. So when you will convert in Newton second per meter square, what you will do? And velocity you need to calculate. L is given 1 meter and your h is given 0.03. It will be square. 8 poise is given. Here I want to write you. Poise 1 by 10 of Newton per. So we'll divide the 10, it will become 0.8. So from here your U average is 0.3 into 10 to the power 4 into 0.03 square divided by 12 into 0.8 into 1. It will be 0.28 meter per second. Now you know the formula of discharge. Very easy. That is your velocity 0.28 into area. Whatever I have just tell you before few minutes back. So it will become 4.2 into 10 to the power minus 3 meter cube per second. This is the whole calculation. Just I have shown you the breakdown of this. Now we'll move on next question number. That is the okay. So match list A and list B. List A is the name of boundary. This is the name of boundary. List B, this is the name of conditions. That is the boundary condition. This is, and this is the your boundary. Okay, where V is velocity, P is the pressure, and tau, or you can say the R. This is R is given. So this is the shear stress. So now you just try to match whether in the first is given fluid in contact with a solid. Like here is a fluid is flowing, but it having the contact with the solid, contact with the let's suppose plate. So this is the first. Second, when two fluid A and B meet at an interface. Let's suppose water is flowing and at the interface oil, oil is there. Here is the oil is there. So at the interface, we are talking about at the interface. The liquid in contact with gas. Let's suppose water is flowing and the air is gas, so it is in the contact with air. So in contact with air. So which type of boundary conditions we'll just follow when we will apply, when we will try to solve such type of problem mathematically. So which option is correct, whether A, B, C, D? Just think on that. Think and try to give your answer for question number. Next question number. Question number 2. Just try to give your answer. You have again 2-3 minutes. Please try to solve. Okay, let me discuss. So here we are talking about, this is the first option A, and this is your option 2, this is your option 3. Not option 3, this is the list. In list A, this is the question 1, 2, 3. That is the fluid in contact with solid wall here, and the when fluid flow, when two fluids meet at interface, that is the fluid A here and fluid B here, and liquid in contact with, here is the air and this is the liquid. So you know already from the boundary condition, that is the no slip condition. No slip condition, it means what? When your fluid is contact with any solid, your fluid velocity will be 0. So it means what? That is your velocity of fluid is nothing but your velocity of wall So this is the meaning here. So your first is linked with P. For first, your correct answer will be P. Now for second, when two fluid A and B meet at an interface, what will happen? The velocity at A and B will be equal to, yes, obviously, and RS, that is the shear stress in A, equal to shear stress at B. Yes, definitely it will be correct. So for second will be Q option. Liquid in contact with gas, yes, the pressure liquid and pressure at gas will be equal at the interface and the contact interface, and the liquid and the shear stress in the liquid will be 0. This is your R. So if you will see, option A will be correct for that. Remember always, please. Next question. The next question is, here is the next question. Velocity component are in two-dimensional irrotational flow are u is equal to this and v is equal to this. Estimate a constant A. A value you need to calculate, this value. The velocity component in two-dimensional irrotational, here we are talking about irrotational, that is your W, if it is given U and V component, so WZ not equal to 0. Irrotational means this. You estimate A and B. You estimate A here only. How you will calculate? Just please think. Then I will show you answer. Just we have the 1 minute. Just think on that. Just I have given you time to think on that. Then after I will just show you the answer. Then whether you will thinking correct or not, just check. How I will approach this type of question. So here is the irrotational, not rotational. If velocity is rotational, this is the condition of rotational. If irrotational, this will be 0. Oh, I think in the previously I was telling just opposite, but in the, if your fluid is rotating, then this rotational component will be exist. If not rotating, that is irrotational, this will be 0. So what is the formula? Just previously I have just shown you del V by del X minus del U by del Y. If it is 0, what will be happen here? This formula will be equal to like this. You just put it del V by del X, it will be del V by del X. If you will do here, it will be AY square minus 0 minus 3x square by 3. So AY square minus 3x square by 3. Now del U by Y square. If you will do here, del U by Y square del u by del y. This will be 3y cube by 3y square minus, this will be 0, plus 0 minus x square. So just put here, if I put here ay square minus 3x square by 3 equal to 3y square minus x square. So this will be 0. So minus x square will be cancel out, and here y square and y square will be cancel out. So it may be a is equal to 3. If this is y cube, a is equal to 3. So I think option is wrong. Y square and x square here is written. Yes, y square and x square will be. If I write these things, this will come ay square and the x square. Okay, same thing. And here that is the 3x square. Okay, this is wrong. So the correct option, if I write here 3, it will be 3. So thank you for today. We'll discuss the week number 11 in the coming week. So thank you for today. We'll meet in the next class on next Monday. So thank you. Bye bye.